Hello, this is a presentation of our article in Formalize 2021 titled Quantifying Faultiness, What Does It Mean to Have N Faults? This is written by Besma, Khaireddine, my co-author in Tunis, and myself, Mili. So it is common in software testing literature to see a program being seeded with N mutations and then declared to have N faults. The problem we have with this sentence is not that it is incorrect, rather that it is meaningless. And because it is meaningless, because it has no meaning, we cannot tell whether it is correct or incorrect. On the other hand, when we try to lend it a meaning, we find that it is often incorrect. Not only is it incorrect, we argue that it is also not very relevant, and sometimes it is actually misleading, and we will explain why. So why are we saying that a sentence such as program P has N faults has no meaning? Simply because to say that a syntactic feature, any syntactic feature in a program is a fault, we must really specify that, we must preface that with 4 parameters. And in order to talk about faults in the plural, to say that we have 10 faults or 20 faults or 100 faults, we must specify one more parameter. And all the bibliographic sources that make declarations such as program P has N faults do not refer to any of these 5 parameters, or if they do, only to some of them and mostly implicitly. So our talk will be structured as follows. First of all, we talk about absolute correctness and relative correctness because we feel that any discussion of fault must be done in relation to some concept of relative correctness. Then we discuss what it takes to talk about a fault, then what it takes to talk about multiple faults. Then how do we quantify the degree of faultiness of a program? And finally, we illustrate this on the case of tcas and conclude. So, absolute correctness and relative correctness. When we identify a fault in a program and repair it, the program does not necessarily become correct. At best, if we did a good job, it should become more correct than it was. That's all we should be able to claim. Therefore, any study of faults must be done by means of and with respect to some concept of relative correctness, that is, the property of a program to be more correct than another with respect to a specification. So that in addition to the traditional well-known concept of absolute correctness, which we know since the late 60s, we also need to introduce and discuss a concept of relative correctness. So before we introduce a definition of relative correctness, we consider what attributes characterize a sound definition of relative correctness. So if I give you a definition, how can you tell that it is any good? And to answer that question, we propose, subject to discussion, maybe you agree, maybe you don't, but these are the list of 4 properties that we feel any definition of relative correctness ought to satisfy. First is reflexivity and transitivity, but not anti-symmetry. Okay, so if I say that a program P prime is more correct than a program P, that ordering that I'm trying to define ought to be reflexive and transitive. We don't want it to be anti-symmetric because we want to consider that 2 programs may be equally correct, but still distinct. And I don't mean distinct syntactically, I mean distinct semantically. That is, they compute different functions, but the 2 functions are equally correct. Second, culmination is in absolute correctness. Obviously, you want that if you make a program progressively more correct, then eventually it will become correct. Alternatively, an absolutely correct program is more correct than or as correct as any candidate program. Third condition, you want to ensure that if P prime is more correct than P, then P prime is more reliable than P, but you don't want to be equivalence. Clear why you want the implication, why you don't want equivalence, because we hate to think that all we did was to invent a new name for what it means to be more reliable. It's also because we think of reliability as a stochastic attribute, and we want to think of relative correctness as a logical attribute. in the same way that absolute correctness is a logical attribute. The fourth condition, and probably the most controversial, is we want to think that if P prime refines P, actually P prime refines P, if and only if P prime is more correct than P with respect to any specification. Okay, so P prime more correct than P with respect to a given specification means P prime is better than P for the purposes of R. But if I quantify this property universally for R, then it becomes a binary property between P prime and P that essentially says P prime refines P. So now that we have introduced the four conditions that we think should characterize any definition, we present a definition and we claim that our definition satisfies the four conditions in question. So given program specification R and two programs P and P prime, we say that P prime is more correct than P with respect to R, if and only if the domain of R intersect P prime is a superset of the domain of R intersect P. Now, this does not mean that P prime imitates the correct behavior of P. It only means that P prime is correct over a bigger input domain than P is. And the picture that you see here shows R in the middle, and on the left you have two programs Q and Q prime, where Q prime is more correct than Q, and it is more correct than Q by virtue of duplicating the correct behavior of Q, which is 1, 2, 2, 3. On the other hand, P prime is more correct than P, but P prime is more correct than P by virtue of a totally different correct behavior. And the reason that's possible is that R is non-deterministic, so there is more than one correct behavior. So domain of R inter P is what we call the competence domain of P with respect to R. That's the set of inputs for which P behaves according to R. And program P is absolutely correct with respect to specification R if and only if its competence domain equals domain of R. Okay, so by definition, the competence domain of any program is a subset of domain R. When it equals domain R, that's when the program is absolutely correct. So I don't expect you to read this, but these are 10 programs that we define. Yeah, sorry, I forgot to write the specification, but again, it probably doesn't matter. And this is how these 10 programs are ordered by relative correctness. So whereas absolute correctness divides this pool into only two categories, those that are absolutely correct, that are surrounded in green, and those that are incorrect, that are surrounded in red, relative correctness orders these programs on a partial ordering. It's actually not anti-symmetric, as you remember, but it looks like a partial ordering. Okay, and the maximal elements of this partial ordering are the absolutely correct programs. Okay, so now that we have a definition of relative correctness, we move on to discuss what does it take to talk about a fault. In order for us to say that a syntactic feature of a program is a fault, we need to specify 4 parameters. First of all, the specification with respect to which correctness and incorrectness are defined. Second, a definition of relative correctness. Third, a level of granularity at which we want to isolate faults. And fourth, a vocabulary of atomic changes. So we review these briefly. The first parameter is then a specification with respect to which correctness, absolute correctness and relative correctness is defined. And clearly something is a fault only because it precludes the program from being correct. So I need to know correct with respect to what specification. The second parameter is a definition of relative correctness, and we adopt the definition we introduced earlier. The third parameter is a level of granularity at which we want to isolate faults. Okay, this should be part of any definition of faults, because if it weren't for that, I could say, well, there are only two situations. Either the program is correct or the program is incorrect, and the fault is the whole program. Okay, but that's not very helpful. Usually we want to isolate fault at smaller levels of granularity. That's why we need to specify that level by syntactic atoms. And we introduce the concept of feature, which is one or more syntactic atoms. Why? Because some faults may span more than one atom, not necessarily contiguous. Okay, so some faults may consist in making two changes to the program before the fault is removed, two or more. And finally, a vocabulary of atomic changes. You can think of them as mutations. So these are a set of pairs of the form AA prime, where A is a syntactic atoms, and A prime is a substitute that I can put instead of A without violating the syntactic integrity of the program, meaning the program P prime obtained by replacing P by A prime is also syntactically correct. Okay, with all these parameters, now I can define what is a fault. So I am given a program P on space S, a specification on S, a set of atomic changes AC, and we say that the feature F is a fault in P with respect to R for the set of atomic changes AC if and only if there exists a feature F prime obtained from F by atomic changes such that P prime obtained from P by replacing F by F prime is strictly more correct than P with respect to R. Yeah, so strictly more correct means this correct, means P prime is more correct than P, but P is not more correct than P prime, okay? And the pair FF prime is said to be a faulty pair of F in P. So here we have defined what is a fault and what is a faulty pair. In other words, a fault is an opportunity to enhance the relative correctness of a program, and a fault repair is the act of turning that opportunity into a reality, meaning that's the act of exploiting that opportunity to enhance the correctness of the program. Okay, so far we have discussed the four parameters that I need to define what is a fault. Now we need to discuss the parameter that I also need to define to talk about multiple faults. And before we can talk about multiple faults, we need to decide what is a unitary fault. Okay, if I tell you that the distance between Newark, New Jersey and Philadelphia, PA is 85 miles, that's because you and I have a common understanding of what is 1 mile, otherwise the sentence makes no sense. Likewise, before I tell you that the program has 10 faults or 50 faults, I need to agree with you what is one fault. So if I consider a program P in which two atoms, A1 and A2, admit substitutes, such that the program obtained after substitution is strictly more correct than P, question, how many faults are we looking at? Are we looking at two faults, A1, A2, or one fault that spans two atoms, A1, A2, or three faults, A1, A2, and the set A1, A2? And if we are going to start counting faults, we better start by figuring out the answer to this question. So a unitary fault is a fault that is made up of a single atom or a fault that is made up of two or more atoms, such that no subset of the atoms is a fault. And the number of atoms in a unitary fault is called the multiplicity of the fault. Okay, so already here you can see why making statements such as program P has 10 faults simply because you have made 10 atomic changes is tricky, because some of the faults may span more than one atom. But that's not the only problem, in fact. Okay, so how to define a unitary fault? Okay, I give a couple of examples here. And again, you don't have to look at the details, obviously. But this program, as well as the next one, deal with two loops, where the loop is written to iterate from 0 to n minus 1, and actually it should have iterated from 1 to n. So two things, you need to change the initialization and the loop condition. Question: initialization loop condition are two atoms. Do I have a fault that spans two atoms or two faults that span one atom each? Okay, in this particular example, which is computing the sum, it turns out if I change only one atom, it doesn't enhance correctness. So I still stay stuck in the red area, and there is no ordering relation between P prime 1 obtained by doing the first substitution, and P'2 obtained by the second substitution. I need to do both before I can obtain a correctness enhancement. In this case, we are dealing with one fault with multiplicity 2. I have another case here of a loop that again iterates from 0 to n minus 1 instead of from 1 to n. It turns out in this case, if I make one change, I enhance correctness. If I make another change, I enhance correctness. If I make both changes, I make the program absolutely correct. Okay. In this case, I have two faults of multiplicity 1 each. Of course, you see three arrows leaving Q, but the middle arrow is actually not a unitary fault, so it doesn't really count. I'm just throwing it because it's there is a relation between Q and Q prime, but it doesn't mean that's a unitary fault. The unitary faults are those going from Q to Q prime 1 and Q to Q prime 2. Okay, quantifying faultiness. We argue that there are three metrics: fault multiplicity, fault density, and fault depth. So we have already discussed fault multiplicity, which is the number of atoms in a unitary fault. Fault density is the number of unitary faults in a program, and fault depth is the minimal number of fault repairs that separate a program from absolute correctness. Observations. First of all, the number of atoms is different from the number of unitary faults, again, because a unitary fault may span more than one atom. The other very important remark is fault density has nothing to do with fault depth. Just because we have n faults does not mean we are n fault repairs away from absolute correctness. It can be more, it can be less. Third comment, fault density and fault depth evolve differently. If P prime is derived from P by a unitary fault repair, then what I know is that the depth of P is less than or equal depth of P prime plus 1. When is it equal? It's when P prime is on a minimal path from P to absolute correctness, but if not, then there is inequality. So while we have this relation for depth, we have nothing like a relation, like a property pertaining to density. Density is all over the map. Fault depth is a better measure of faultiness than fault density, which means that fault density is actually not very relevant. And this refers to my comment earlier in the talk when I said that counting the number of faults is not a very relevant metric. Why? Because the real relevant metric is how many fault repairs separate you from correctness. So let's see, to illustrate briefly the contrast between density and depth, I take an example here. I think it's still the example of doing the sum of an array, and I can correct it. Okay, so I can correct it by changing the initial value and the loop condition, or by changing I into I plus 1. So I have really two faults. But the trouble is, if I fix any one of the faults, the other is no longer a fault. And if I am so misguided that I fix two faults, I will end up with another program that has two faults. So what we are dealing with here is a fault density of 2, because I have two faults, and a fault depth of 1, meaning I am only one fault repair away from correctness, which explains why we argue that the number of faults is misleading, because you tend to think that the more faults you have, the worse off you are. Actually, no, the more faults you have, in this case, for a given fault depth, the better off you are, because it means you have more options to reach absolute correctness. This is another example. Remember, we said that the fault depends on the specification, the atomic change, the syntactic atoms, the atomic changes, etc. This is an example that was in the original paper. Unfortunately, we had to remove it because we had to shorten the paper. But this shows how, by varying the program and the specification and the set of atomic changes, we change completely the configuration of the faults, and we change the density and the depth in each case. So we have different graphs for different situations. Illustration. if I apply 8 mutations on tcas, what do I get? So we take the tcas component and we apply 8 changes to it, and then we discuss how many folds does it have and what is its fold density, fold depth, fold multiplicity, etc. So tcas, for those who don't know, it's a component from the Siemens benchmark. It has 173 lines of code in C language. It actually, in the benchmark, there are 42 mutations, but we apply only 8 of them that we call M1, M2 until M8. And the seeded program, so the program to which we have applied all these 8 mutations, we'll call tcas star. And what you look at the table here is the changes that the mutations in question, their location, and what is it that we change to what. So if you look at the original column, that's the atomic, that's the syntactic atoms. And if you look at the pair of columns original change, that's the atomic changes. Okay, so with this situation, we take tcas star and we try to apply mutations to it and to build all the repair paths from tcas star to a correct version of tcas. So the specification that we're using is the pre-restriction of tcas to the test data T, which I think is about 1600 data. The level of granularity is what I showed you earlier, the third column of the mutation table. The atomic changes are the, the atomic changes here are the reverses of the changes that were applied to tcas to obtain tcas star, okay? We are reversing the mutations. That's how we attempt to repair the program. Relative correctness is what we defined, and unitary faults is also what we defined. Now we know how to count faults and how to count fault repairs. So starting with tcas star, what we do is we take tcas star, we apply all the mutations M1 inverse, M2 inverse, M3 inverse, etc. until M8 inverse, and we see if any one of these strictly enhances the correctness. If it does, we look at what we get, or the new mutants that we get, we apply to them further mutations, we see how many are successful, climb, until we reach the top of the graph. And the top of the graph is what you see here. What's important to notice here is that each node in this graph is a mutant of tcas. The bottom of the graph is the tcas star, which is the version of tcas that is seeded with the 8 faults, or the 8 mutations, apologize. The top is 2 programs, 2 versions of tcas that are absolutely correct with respect to tcas pre-restriction T. Every arc in this graph represents a relative correctness, strict relative correctness property, meaning every arc really represents a fault repair achieved by the mutant that, the mutation that you see there. And again, all the mutations are inverses of the original mutations. What is very important to notice is that the outgoing node of each, the outgoing degree of each node is the fault density of that node. And the distance from a node to the top is the fault depth. So you notice that tcas star has fault density of 4. Even though we have made 8 mutations to it, it has only a fault density of 4, not 8. You notice also that the fault depth decreases by 1 each time we climb by 1 layer, whereas the fault density doesn't obey any law. Sometimes it increases, sometimes it stays the same, etc. And in contrast with the declarations that tcas has 8 faults, this is how we see a serious report on the faultiness of the program. We explain what specification we're using, what is the relative correctness, what is the granularity, what are the atomic changes, and we give in return the density, the depth, the multiplicity, and the sum of multiplicities. Finally, saying that a program N has a program P has n faults does not mean much per se for the following reasons. First of all, missing context, the various parameters. Second, missing unit, the unitary fault. We also argue that the number of fault is the wrong attribute and that faults should be defined in such a way that they are attributes of the program rather than what we think the programmer meant when he or she wrote that. Main finding, the study of faults must necessarily involve the concept of relative correctness. We define relative correctness by comparing competence domain. It is important to distinguish the difference between fault multiplicity, density, and depth. Also important to recognize that depth is a better measure of faultiness than density, and consider the implication of all this for testing, repair, and reliability. Thank you.
Okay, welcome back. I'm here with Professor Ali Mili. He's a professor at the New Jersey Institute of Technology, and well, welcome here, Ali. Thanks for your nice presentation.
Thank you, Nico.
We now have time for a few questions and for a few questions. I see there are a few questions in the chat. I'll start with those. First question is by Simon Blutze. And the question is the more correct pre-order a pre-congruence? If substitute a module by a more correct one, does that make the global program more correct?
Yeah, I'm not sure I understand the pre-congruence. If pre-congruence means a relation that is reflexive and transitive but not antisymmetric, yes. Meaning there are equivalence classes of programs that are equally correct, and they are ordered between equivalence classes, the answer is yes. Does a substitute a module by a more correct one? Does that? I have no idea. I don't believe so, because that depends on R, and that also depends on how the module is composed within the overall program. So the question is, the answer to the second question is, I am not sure.
The answer to the second question. Then I have a question for you. In your talk, you characterize a fault as an opportunity to enhance the relative correctness of an incorrect program. So this portrays a fault in a positive light. How do you justify this?
So when I say that the fault improves the correctness of an incorrect program, the bad news there is that the program is incorrect. But the good news is that there is an opportunity to enhance correctness. So if you imagine, for example, different atomic changes where one set of atomic changes does not allow you to enhance correctness, that's where the bad news is. But having the opportunity to enhance correctness is actually the good news part. And that relates to the distinction between fault density and fault depth. People, I think of fault density as a measure of faultiness. It's actually the wrong measure. The real measure of faultiness is how many fault repairs separate you from correctness. But for a given fault depth, having more faults is actually good, because it means you have more opportunity to enhance correctness. I know this is counterintuitive, but that's what we believe. And incidentally, the second question of Simon is, how does one identify relevant atomic changes? Well, these are the mutations that are available to you to enhance correctness. So that's how it is. It comes into the picture.
Okay, and you already said something about fault density and fault depth. How do you explain the difference between these two in the tcas experiment?
So in the tcas experiment, I don't think I have time to show my screen, but you can think of the outgoing degree of every node as being the fault density, and the distance from that node to the top as being the fault depth. Okay. And the remarkable thing is fault depth decreases with every fault repair, but fault density does not, which is another reason why fault depth is the correct measure of faultiness, not fault density.
Okay. Well, we have a few more seconds left because we're taking automatically to the discussion room. If you want to join us there to ask Ali more questions, then you are more than welcome to do so.